So I usually build two different types of TreeNet models. One I've called a full TreeNet model, the other one called a simplified TreeNet model. And for the full one, it's basically what I've done is just put all the predictors in and build a model. You end up with a variable importance list, and some of those variables that you put in will not have any importance. I then build a second model using only the predictors that were identified as important in the first one, and then build another model. And I do repeat the process until the final model has got a variable importance list that remains unchanged. And the reason for doing this is just that it acts to reduce the total number of important variables, and it often usually improves model performance. So if you look at diagnostics on a holdout sample, they've often improved by the time you've done that. The second model is simplified TreeNet model, and the aim here is just to try and cut down the number of predictors even further. So typically you still may have 100 important predictors or something, but in your full model. So it's very difficult to build, or very time consuming to build a GLM model with 100 predictors. So the aim in the simplified one is to get another model that has got far fewer predictors. It's usually very much a trial and error approach of removing variables. I mean, there's some obvious things to do. If you've got a number of variables which you think are highly correlated, you can only just keep one of the group of correlated variables in your model. And then it can start arbitrarily leaving out some low importance variables and rerunning the model. And the aim is to reduce the number of predictors and not to have too much degradation in model performance. And so this is an example of assessing the model performance. So the performance was assessed on a holdout data set, so it hadn't been used in the modeling at all. And this shows a gains chart. There's two gains lines here, one from the full model, which is a blue line, and one from the simplified model, which is a red line. So the simplified one has got a lot fewer predictors, only 20 variables, compared to the full model, which had 100. And you can see on the gains chart that the red line, the simplified model, is slightly underneath the blue one, but we've kind of assessed that degradation in performance as we can live with it. The other useful thing about TreeNet is to use it for feature identification, and partial dependency plots are a very useful way for feature identification. And Mikhail gave some examples yesterday of identifying the main effects features using the partial dependency plots. You can also use them for identifying interactions. I mean, it can be quite a time-consuming process. It involves looking at two-way partial dependency plots and slicing them up and looking for changes. I hear that Dan Steinberg has been working on a better method for doing this, and I think he'll be talking about it in the last session. But what we've done in the past is done the two-way partial dependency plots, and here's an example where I've given the partial dependency plot for policy renewal as a function of the distance from competitor. And I've done it for two different segments of the data, one for policies have a particular characteristic, which I can't mention, another one, a group of policies which don't have the characteristic. Oops. And you see that here the customers are obviously not very sensitive to movements from competitors, but here they are. So that's obviously an interaction effect, and it's something we can use or inform our model building when we build the GLM. So having built the TreeNet model, we're now in a stage to kind of transform that model into a GLM model that we can implement. Now you might be thinking, why bother building a GLM once you've got a perfectly good TreeNet model? Well, first of all, for those of you who don't know, what is a GLM? Again, many other talks have covered this in much more detail and much better than I could do it, but I'll just give a basic flavour for it. So a GLM is just a standard statistical modelling technique for regression problems such as renewal modelling. And the main difference between GLM modelling and data mining techniques such as TreeNet is that with the data mining algorithms, the algorithms can identify and model the complex of the features almost automatically. So the algorithms will, automatically change their architecture to match the data. So with GLMs, you actually have to manually build the architecture. So you have to sit there and construct an architecture which you can use then to model the data. So obviously that takes a lot more time and a lot more effort and is a lot more difficult, so why bother? And the main reasons are you end up with a model architecture that tends to be a little bit simpler than the data mining model. So what I mean there is that for the GLM you can write down a relatively simple functional form, which is a bit more difficult to do for the TreeNet. And this is particularly important when you come to explain your model to management. And particularly in insurance companies, there's been a long history of GLM use, and managers are often quite comfortable with GLM, so it makes it very easy to explain to them. Also, the model architecture tends to be relatively stable when you refit the model to new data, which makes model management a bit easier. And it means that when you're explaining changes in the demand model to management, the changes can be explained in terms of changing parameter values rather than a new model, and that can be easier for management to accept. It can give you a bit more control, so if you need to extrapolate outside the domain of data that you fitted to, you can do that a little bit more easily with a GLM, or at least you can easily put in the behavior you want to extrapolate. And finally, it's easier to deal with policies which seem to have apparent negative price elasticity. And what we find with many data sets, when you fit a data mining model to them, you'll have regions of negative price elasticity. And what that means is that for some sections of policies or some policies, if you increase the price of those policies, people will buy more of them, which is a very strange thing. I mean, that kind of behaviour happens in some markets. For luxury goods, for example, you increase the price of a luxury good, sometimes people will buy more of it. But insurance is not a luxury good. Or you'd be very sceptical before you expected to increase the number of people bought by increasing the price. So when you see that, usually it suggests there's something a bit funny in your data. I mean, there's a lot of components which go into your data. You've got models of competitors, for example. And it's not always easy to correct the data, but you can, at least with the GLM structure, you can start to impose some of the behaviour you want to see, and it's a little bit more easy to do. So that's just a brief overview of the reasons that why we go to the effort of building a GLM. So I'll just give you a little bit of a flavour of the kind of things you see in the renewal rates. These are only the obvious ones, of course. And just to give a flavour, I've given some average fitted and observed plots by different predictors. So this is the average fitted and observed plot by competitive distance. So what this shows is, when the distance is negative, your price or your insurer's price is much further away from competitors. When it's positive, when it's negative, your price is much cheaper than competitors. When it's positive, your price is much more expensive than competitors. And you see you get kind of the nice downward behaviour as that you'd expect. As you get more expensive, the renewal rate drops. So measurements of customer loyalty are important. So obviously the longer a customer has been with you, the more likely they are to renew with you. And that's seen here. And age also has a influence as well. So as people get a little bit older, their renewal rates tend to go up. And there tends to be a drop-off at old age as people either die or stop having their own home. So all the way through the GLM model building stages are constantly, assess it compared to our TreeNet model. And this is one of the assessment plots that we would typically use. So this is another gains chart. Again, this gains chart was done on a holdout sample, and there's two lines here. One, the GLM, which is the blue line, and the other one is a TreeNet, which is the red line. And you can see they're virtually indistinguishable, so they're both giving similar model performance.